Hi. Okay. All right, so let's get started. We're just going to do a quick review of chapter 4. This is gravitational attraction as well as friction. All right, so we were taking a look at gravity and gravitational attraction as well as friction and a few other things. Okay, so we'll start with gravity. Now, Newton's law on gravitation. Okay, of course, this is chapter 4 that we're talking about. Now, Newton's law on gravitation, the first part of it we've already taken a look at. The first part of the law, which was Fg, which equals to mass times gravity. Now, remember what we said. This is when an object is on the surface of Earth. When an object is on the surface of a planet, any planet. Now, the question that you got in the quiz yesterday was of a person on the sun. Okay. Now remember, gravity is dependent on wherever we are in the universe. Okay. So whatever the gravitational attraction is, that would be what your gravity will be. Okay. So if I'm on the moon, of course, my gravity will be whatever it's on the moon, which is 1.7, I think, meters per second squared. If I'm on Mars, my gravity will be 3.4 meters per second squared, and so on and so forth. So if I ask a question about how much you weigh on a particular planet, you cannot use 9.8, right, twinsies? Okay, you can't use 9.8. Okay, so you have to use the gravity of that planet. Now remember, this is on the surface of a planet. And we're not talking about mass, we're talking about weight. Now remember we said this right here is the weight of an object. Okay? In reality, we can't actually measure this unless we're on the surface of something. Okay? So on Earth, we're not really actually measuring Fg. What are we measuring? If you think about it. What are we measuring? F normal. When I'm on Earth and I stand on top of a scale, gravity is pulling me down, but it's the F normal that's pushing back against me. So I'm actually weighing myself using F normal. I'm cheating. Okay? Which equals to Fg. But I'm going to give you scenarios where they're not equal to each other. And we need to talk about that. That's kind of important. Okay? In an elevator and so on and so forth. So here, my Fn and my Fg are equal to each other because my object is not moving. That's why we use this on the surface of a planet. It is pretty straightforward. Okay. Are we good with this? So the second part of Newton's gravitational attraction is when he looks at when you're far away from the surface of a planet, or if you don't know the gravity of a planet. Let's say I don't know the gravity of a planet, and I want to find out the gravitational attraction between two objects. Then he said that I will use this formula, which is G mass 1 mass 2 divided by R squared. R squared, not R2. R squared. Okay? And here, big G was a universal gravitation constant. Universal gravitational constant. Okay. It was derived by a scientist. It's in your textbook. I don't remember the exact name of it. Right now, I totally forget what it was. So this is 6.67 times 10 to the negative 11. Now this is already given to you on your formula sheet. So you're not memorizing this, number one. Okay. Mass 1, of course, is your first mass. Mass 2 is your second mass. Okay. And R, what was R again? The distance. Okay. So the distance between the two objects, between the centers of both objects, in meters. Very important. This is in meters. It's not in kilometers, it's in meters. Okay? I want to do one question for this, just so that you have a question that you can look at for studying for the test. Okay, So if we were to do this question, then I would just do Fg, which equals to 6.67 times 10 to the negative 11 times 5.98 times 10 to the 24. And this right here is 7.35 times 10 to the 22 kg divided by my distance between the two would have been 6.38 times 10 to the 6 plus 3.84 times 10 to the 8 plus 1.7 times 10 to the 6 squared. And they would be your Fg. I don't know what that is because we don't have time, so we're not going to go over it. Okay, that would be Fg. This is an example of what Fg is. Remember, this has to be in meters. Most important. Meters, meters, meters. Very, 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 very important. Okay, all right. So that's an example of universal gravitation, the attraction between the moon and the earth in this example. Okay, all right. So I'm going to erase this. The next thing I'm going to take a look at is friction. Okay, now friction is one of the most important properties that we have on Earth, which causes and affects our motion. So we have two kinds of friction: F kinetic friction. Okay, of course, opposes motion, which means it is always opposite to direction of motion. Okay, and Fs, static friction, okay, also known as starting friction. Yeah. No, it's not. Mic is still on. See? Okay, so static friction or starting friction, this is the minimum force required to get an object to move. Okay, so these are my two forces that we're going to take a look at in terms of friction. Then we looked at this right here, mu k, which is the coefficient of kinetic friction. Okay, and this, of course, is the formula is mu k equals to Fk divided by Fn. And Fn, of course, is equal to, in our situation, your gravity, equal to gravity. If my object is on the surface of a planet, on the surface of Earth, so your Fn is going to be Fg, which is going to be mg. Okay, mu s is going to be Fs divided by Fn. Okay, and of course, again, Fn equals to your Fg.